Learn how to create SAP 2000 style animated eigenmodes with Gmesh and OpenSea's PY. Stay tuned. Hello from Chile, I'm Jose Abel, civil engineer, and today we're going to continue with one of these short Gmesh to OpenSea's tutorials where we merge OpenSea's PY with Gmesh to create awesome analysis. So we're going to start two videos from before this one with the video where we did animation of transient analysis. So in this case we're going to be using the same mesh, but we are going to be wanting to plot the deformed shape according to eigenmodes of the problem. So I'm starting here with example 3, which if you haven't seen that video, the link is in the description so you can see what that is all about. I've added some new functionality to Gmesh to OpenSea's library, so you should check out the new code and bring in those changes so you can use this tutorial. Okay, so let's close this animation for now. And I'm going to start with example3.py. I'm going to rename it to example5.py because this is the fifth video in the series. We're going to be reusing the same example3 mesh, and everything is going to be pretty much the same. So we're going to add the nodes, we're going to add the elements, fix the nodes. What we want to do is change the analysis type. So instead of doing a regular transient analysis, we want to actually compute the eigenmodes. So let's get rid of this stuff over here. I'm not going to be doing a transient analysis. Instead, we're going to be doing an eigenanalysis. So that's very simple in OpenSea's. We can get the eigenmodes by issuing the eigen command. We still need to set up a transient analysis, and we still need everything else that we had, except the loads. We could comment this out because eigenanalysis does not take into account the loads, but you do need the fixities. So we're going to request 10 modes. Let's add a little variable that we call nmodes. Let's request 10 of those. And the output here, you want to not only compute the eigenvectors, we need the eigenvalues, which are our frequencies. So this eigen command returns a lambda. Let's use the Greek letter lambda, and I can do this in Sublime Text because of the plugin I'm using. So in this lambda vector is going to contain all the eigenmodes. So let's just print that directly and see what it looks like. Here we go. Let's be fancier than that. Let's use our new Python features, f-strings. Here we go. So when I run this, I need to run it on a terminal actually here. So where's my terminal? My terminal disappeared. Okay, here we go. Let's open a new terminal and Python example5.py. And let's ignore that for the meantime. So you can see here are the eigenvalues, right? So let's do something a little bit better with this. Let's do for lambda value in, so lowercase lambda in uppercase lambda, and let's print f a certain amount of things. So I want to compute, for example, the omega. So the circular frequency is going to be the square root. Do I have the square root imported? I do not have the square root imported, so let's import that from NumPy, import square root. So we're going to compute the square root of lambda. There we go. So that's going to be our circular frequency, and our regular frequency in hertz is going to be omega over 2 pi over, here we go, 2 pi. Let's import the keyword pi too. And then the period is going to be 1 over f. So let's report all these things. 1 over f. So here we go. We have omega. And we have f. This is going to be in hertz. Omega is going to be in radians per second. Hertz, capital H, proper name. And the period is going to be in seconds. And let's also create an enumeration here so that we can enumerate the modes. Let's say enumerate, like so. And the mode number actually is going to be I plus 1, because Python is zero based in its indexing, whereas we want the modes to be numbered. There we go. So when I execute this, let's not run this little thing so that I don't get a Gmesh pop-up. Yeah, you can see the modes. So this is a rather stiff structure, obviously, because it's a big metal thing, right? So you're going to see that the fundamental frequency is 147 hertz, and that's equivalent to a period of 0.006 seconds. Okay, so this is fine. How do I visualize them? How do I visualize the modes? I'm glad you asked, because I just added a new function to Gmesh to OpenSeas that lets you visualize the modes. So this function is very easy to use. You just call it right after you run an eigenvalue analysis, and it's going to help out with everything. So I'm just going to go ahead here and add a little bit of code. So we're going to be running Gmesh here, and I'll explain what's going on. So visualize eigenmode in Gmesh. We're going to add as an input the model, the mode number, the mode I want to plot in base 1, right? And I'm going to, so this is the second argument, and the third argument is the frequency. So this is the frequency of the mode. That's just so that we can have a little text, and we can have this little value here, animate equal true, so we can make some fancy animations. If I just run this like so, I get this kind of plot. So this should be our mode number 10. This is what it says here. How many modes do I have? I'm plotting mode number 10. And the reason it's doing 10, it's because that's the last one we're plotting here. Okay, and then I can press play, and this will get animated SAP 2000 style. I'm sorry it doesn't make the same music as SAP, but hey, this is very cool. Let's go for that first eigenmode. Also, check out that it's reporting the frequency here. So let's go for mode number 1. If we set this variable mode number to be equal 1, it's gonna work just as expected. Here we go. That's the first eigenmode for this structure, and you can see it animated. Animating the modes is a very good idea when you're getting a feel for a structure, because you really get to see what the modes look like and get a good understanding of the dynamics. It's something you cannot get out of a static image. Let's see, you can do several at the same time. So if I do several calls to this, let's go for mode number 2 and 3. This should work. Let's check it out. I haven't tried this, so we'll see what happens. Yay! You can see both modes at the same time. And if you animate them, it's actually going to display 2. So this is fun if you want to compare modes. You can see that the mode number 3 is a torsional mode, whereas mode number 2 is another translational mode. Let's do 1, 2, and 3 so you can see what happens with the first, second, and third mode. So let's do one more thing here, and before I finish the video, here we go. Mode 1, 1, 2, and 3. No, I'm running the wrong example. There we go. And this is fun because we can compare mode 1 and 2, and let's see what happens. So you can see these modes are actually orthogonal to each other. Now, depending on your eigensolver, on what's going on, you might get linear combination of these two modes. You can see they have the same frequency. So they're orthogonal modes that share the same frequency. Eigensolvers tend to, not, I wouldn't say struggle, but have a hard time distinguishing. So they'll find one first, and then the second one is an orthogonal to this one. So you might get a different picture from this, depending on what your computer does. The first mode might be the other one, so beware there. When modes are similar, and especially if you have different orientations, so if it's a perfectly symmetrical system, you might get a mode in the x direction, or in a mixture of the x and y direction, or in the y direction, and the other one orthogonal to that. That's the important part. And our mode 3, if we animate it, you can kind of see it there, doing its twisty little thing. Okay, so that's all I wanted to show for this video. Have fun animating your eigenmodes. For our next video, what I'm going to do is going to explore a little bit into Rayleigh damping and show you how to set up some Rayleigh damping and what it means to set up a Rayleigh damping for your frequencies that are not the ones that you're choosing. Anyway, that's upcoming. See you in the next video. Goodbye.